My name is Izzy. I lead a microscopy group in the University of Leeds, and I guess I'm trained as a microscopist, but the interest is really in applying it to understanding biology. And we look at these sort of curious cell types that are obscured. These guys, which are muscle cells in the heart. They're long, they're like bricks in a wall, long cells and quite large. And I guess I thought this is a good place to introduce them because the microscopy, the biology, and sort of my journey as an LGBT person they all sort of kicked off around the same time. So I thought a good place to start is this picture. So this is the city that I call home. It's Auckland in New Zealand. It's a city that's built on basically a bed of volcanoes, about 50 volcanoes in that city. And it's a good place to start because it's essentially a physical map of my journey. So this here is one of the volcanoes in Auckland. It's called Mount Eden. I used to live just to the east of that, just here. And about 10 years ago, I started a PhD, actually a bit longer than that now, just over here, just to the north of it, in the University of Auckland. And that's where I started to look at heart cells and to learn my ABC of microscopy. Mount Eden was special because it was sort of the top of Mount Eden that I came out to my girlfriend at the time, about 11 years ago. And so if you could capture one place where all these things started, it's a long way from here. This is it. And it's a special place because I think we talk a lot about all the chaos in the world. New Zealand in some ways is a special place because they pioneered a lot of things. So they had their first trans member of parliament in 1999. They were the first country to allow women to vote 125 years ago. So I guess it's a place that I kind of think of very fondly. But the work that has just taken me out of New Zealand is this, the idea that these cells are powerhouses they're like motors, but they're also powerhouses in signaling. And these flashes that you see, this is a cell, a long rectangular thing, and the flashes that you see are signals that happen within the cell, and these signals are the code for these cells to contract, and that's what squeezes the blood out of the heart. And each flash comes from one of thousands of signaling stations that are right throughout the cell. And you can kind of think of it like beer on tap. So, basically they're very good at releasing this signal, and it's calcium, when you want it to. And the taps that we're looking at, sorry, that's really bright, are these guys. So these are, in the world of molecular biology, these are giant proteins. This is a giant calcium channel called the binding receptor. So this is the side view and this is the top view. They're so big that you can actually see them with microscopes. Those of you who are familiar with electron microscopy, you can actually see them with the EM if you isolate them. And in an ideal world, in a clean environment, they form this kind of pattern like a chessboard. And for a very long time, people thought that this is how they are organized in the working cell. And when I was starting out my work, there was evidence that it wasn't the case, and I wanted to find out exactly how they were organized in the intact cell. So we turned to microscopy, but I turned away from electron microscopy at the very beginning and turned to optical microscopy. Now, one of the problems when you're trying to image proteins is that they don't have any color, or they don't have anything that you can see. Now this is upcoming is the slightly gory slide. It's a slight tangent, and it's the fact it's a point. It's an example of showing that biological structures, material, don't have contrast or color. So pretend that you're a surgeon. You just stepped into the theater. Sorry. And you have to remove tumors in that area. That's when you sort of reach for your drink, and something as clear as this, you're trying to cut out the things that you don't need, but keep the things that you do need. But what if you could help your case by giving it a bit of color? And so what you see here is a solution of dye, and it's not just normal dye, it's fluorescent dye. So it glows. Sorry. And so if you could stain that, now you know where exactly the tumors are. Now imagine if you didn't have that. For example, you cut out the things that look quite obvious, but miss those ones. That's not very helpful. So that's the same principle that we use. Instead of tumors, we stain the proteins that we're interested in. And this is sort of a backward view of what we've achieved. So around the time that I started studying back in Auckland, this was a very state-of-the-art image of how those proteins were clustered. So each of these blobs was a cluster of those proteins assembled into what we thought was an array. At the time, we used a new method that there was a step change in the level of detail that we could see. So it's the same structure now with a bit more detail, about 10 times more detail. And more recently, we've gone another step up now to be able to see these smaller blobs. So they're still blobs, but they're smaller and they're a bit clearer. And these, now we know, are these single channels. And this process, I guess people call them super resolution microscopy. But it's a big umbrella term. There are lots of different ways of getting to that. But I guess to summarize how we get to that is, here's an example. I'm not sure, Joss, if you can see this.
I've seen the slides before.
You've seen the slides before, sorry, I'm confusing. But this is a cell that's now stained for this fluorescent dye. This is a conventional way of looking at it. You look at all the dye molecules at the same time. But what if you could look at a few at a time? So you make them flash on and off. So it's a bit like saying, well, if I gave you one of these to all of you in this room, and I shone a great big bright torch from over there, but rather than everyone holding it up at the same time, you take turns, so a few at a time. That allows us to pinpoint the position of where each drink is. Here's a slightly better example. So you probably know what this structure is. So everyone's seen perhaps movies of flashing lights on the Eiffel Tower. But if we could now on each flash mark out the position of that flash and then start to accumulate it, watch what happens. Over time, what you get is a sharper image, and that image has a lot more detail than what the camera lens could do. And this is recorded with a cell phone camera, but you could probably get something that's comparable to an SLR. So that's the same principle. So that is one way of answering this question. This is a very European way of doing things. So Stefan Hell was one of the 3 Nobel Prize winners for this idea. But there's an American way of doing things as well. It's just very different ways of approaching the problem. And the other way to approach it is that if you can't see the small structures of the cell, make the cell bigger. And so this is a new method that's come out of an American group called expansion microscopy. And the idea is that you have a cell here, and this is what you want to get to. So you still tag the proteins that you're interested in with these fluorescent dye molecules. You embed the whole thing in a gel, a hydrogel, and you cross-link the dye molecules to the gel, and then you get rid of the cell. You're not interested in the cell, you're only interested in the dye molecules that you're going to add. And so you digest the whole thing away with nasty enzymes. And then you add water. And I'm going to show you an example of a failed experiment. So these are 2 gels that started life inside a small 0.5 milliliter tube. There's one there. There's the other one that's been hydrated. Now it's a failed experiment because if it worked, this would have been, flowing over the dish actually onto the bench. You can actually make it grow about 3,000-fold in volume. And that means now, because everything's grown and everything's further apart, you don't really need this sophisticated way of switching the molecules. You can actually look at them with standard microscope, benchtop microscope. So I kind of leave you with this kind of a catalogue. This is sort of the techniques, the microscopy methods that I've been fortunate enough to use in the last 10, 12 years. So this is where I started. That was state of the art when I was doing my PhD. Towards the end of that, this was very exciting. And this is a method that we use now. This is sort of state of the art. This shows you in no uncertain terms single proteins. But this is the expansion microscopy method, which now matches what we can see here. And I guess it's a nice thing to now step back and look at it and see it as a journey, because I kind of use this anecdote in the seminar. There's an anecdote that the difference in the level of detail between this image and this image is similar to being legally blind. So if you're legally blind, you'd see that. And this is what you'd see if you had 20/20 vision, but about 2 or 3 times better than what you'd have at 20/20 vision. So it's an improvement in the level of detail by a factor of about 20 to 30 fold. So that's where the technology's at. I'm still here. So that's that. So I sort of just finished up with a few key people who helped this journey. So this was Christian Soller, who was my PhD supervisor when I was in Auckland. On and off, I've worked with him for about 13 years. When I came out, I was very worried that that was one relationship that I didn't want to break down, but he remains one of the most closest allies and collaborators. And I've got a small team now in Leeds doing some of this work, and Tom is sort of has pioneered some of the more recent work, the expansion microscopy work, and a bunch of nice collaborators in Leeds and back in Auckland. So, and thank you for your time.